Okay, lesson 22 is on fundamental identities and proving basic identities. So when you think about different topics or different subjects, for instance, when you think about geometry, a lot of people remember proofs from geometry. When you think about precalculus, the thing that people remember are identities. So I'm not saying that they're the hardest thing in precalculus. I'm just saying that they can be a little bit tricky at first, and there's lots of different ways to do them, just like in geometry, how there's multiple ways to do a proof. Okay, so don't think that if you're doing something a certain way and your friend's doing it a different way, don't think that you're wrong just because you're doing it a different way. Okay, so these are very similar to proofs in geometry. All right, so fundamental trig identities. Most of these you already know. So we're going to start with the reciprocal identities. You know that sine is the reciprocal of 1 over cosecant. Cosecant is the reciprocal of 1 over sine, or it's the reciprocal of sine, so it's 1 over sine. Cosine is 1 over secant, and secant therefore is 1 over cosine. Tangent is 1 over cotangent, and cotangent is 1 over tangent. Okay, so hopefully you already know the reciprocal identities. Okay, the quotient identities, if you see tangent, you know tangent is not only 1 over cotangent, but we also write tangent as sine over cosine, right? Which you've definitely done before. And therefore cotangent, since it's the reciprocal of tangent, it's going to be cosine over sine. Okay, and then we have the Pythagorean identity. Okay, this is one of the most important ones. Okay, and there's actually 3 different versions of it. So I'm going to write the first one, and that's the one I want you to memorize. So the first one is that sine squared theta plus cosine squared theta is equal to 1. Okay, so when I'm writing sine squared theta, what I mean is sine of theta is being squared. Okay, but the way we always write it is sine with the squared there and then theta, just so you don't get confused between sine of theta squared, right? So it's theta isn't being squared, it's the whole sine of theta. Okay, so that's the first way we write the Pythagorean identity. And like I said, this is the one that I want you to memorize. You should always see that and be like, oh, sine squared plus cosine squared equals 1 every single time. Okay, but let's say we divide everything through by sine squared theta. And we divide every single term. Okay, if we did that, then we'd have sine squared divided by sine squared. Well, that's going to be 1. And then we have cosine squared theta over sine squared theta. Well, that's going to be cotangent squared theta. And 1 over sine squared theta is going to be cosecant squared theta. So that's what we get when we divide everything through by sine squared. Okay, that's the second form of the Pythagorean identity. Okay, and then the third form is if we don't divide by sine squared, instead we divide through by cosine squared. So if I divide every single thing through by cosine squared, then think about it. So I'd have sine squared theta plus cosine squared theta equals 1. So now when I divide by cosine squared everywhere, I get tangent squared theta plus 1 equals 1 over cosine is secant squared theta. Okay, so those are the 3 different versions. So even though I've been a math teacher for, gosh, who knows how long, 11 years, I still don't have the second 2 memorized. I don't even care. Like, I can just find them very quickly by dividing through by sine squared and cosine squared. Okay, the one that I have memorized is this first one, so that's the most important one. So the question is, well, where does that come from? So if you think about your unit circle, so I'll kind of skip ahead a little bit. So where it says question, think about the unit circle. Why is the main Pythagorean identity true? So on your unit circle, we know that for any theta, the x value is your cosine and the y value is your sine, right? So that's the point cosine theta, sine theta, which means that you go over cosine theta and you go up sine theta. And we know the hypotenuse is 1. So with the Pythagorean theorem, we know that the x squared plus y squared equals 1, right? So our x is the cosine, and our y is the sine, So cosine squared theta plus sine squared theta equals the hypotenuse squared, which is 1. Okay, and we have it. So that's why it's true. So that's why we call them the Pythagorean identities, because that's all you're doing, Pythagorean theorem. Okay, the next thing are the cofunction identities. Okay, and this is something that might have confused you before, why sine and cosine weren't reciprocals of one another. Everybody always thinks that sine is the same as 1 over cosine. That's not true. Sine is 1 over cosecant. So people are like, well, why? What's the relation? And this is what it is, the cofunction. So when you see cofunction, I want you to think complementary. Complementary. Put extra N in there. Complementary. I don't know what I'm doing. Pretend I can spell complementary. Okay, there we go. Anyway, so we have cofunctions are complementary angles. So when you see sine of pi over 2 minus theta, pi over 2 is really 90 degrees, right? What that is the same as cosine of theta. Okay, and likewise, cosine of pi over 2 minus theta is really the same as sine of theta. Tangent goes with cotangent, it's cofunction, so this is going to be cotangent of theta, tangent of theta, secant is cosecant, and cosecant is secant. Okay, and that probably doesn't make much sense right now, but let me give you a little example here. So if you see something like sine of 40 degrees, it is equal to cosine of its complementary angle, cosine of 50 degrees. Okay, so that's what we're saying. Okay, we could also think about the graphs. Sine and cosine are both graphs that go like this. Cotangent and tangent are graphs that go like this, or cotangent, goes down. And then secant and cosecant are the U ones, right? So they're the up and down, and so on. So their graphs look the same. And what this actually means is that they're the same as long as you shift. I had to write it in a different way. So I have to write it like negative theta minus pi over 2. So if you shift right pi over 2 and then reflect over the x-axis, the graph is the same as cosine, which is really kind of strange, but you can play around with it, and I think you'll see that it is true. Okay, so those are the cofunction identities. And then the last ones are the even and odd identities. So if you think about sine of negative theta, it's almost the same as sine of theta, except they're opposite each other because of the even and odd thing, which we've talked about before. So if I draw the sine curve, right, if I talk about sine of 30 degrees and sine of negative 30 degrees, they're at different heights. One's a positive height, one's a negative height, so they're opposite each other. You could also think of it on the unit circle, right? At 30 degrees, my sine value is 1/2. At negative 30 degrees, my sine value is negative 1/2, right? So you could think of it that way as well. So let me write that a little nicer. So negative sine of theta. Okay, but if you talk about cosine, the cosine at 30 degrees, or any angle, is the same as its negative. So this is equal to cosine of theta. So we don't have a negative up front. And then tangent is also odd, so it's negative tangent of theta. Cotangent is odd, because it's the same as tangent. It's just a reciprocal. Secant is even like cosine. So they're like the reciprocals are either even or odd, just like the original one was. Okay, and then this is negative cosecant. Oops. Okay. So really all you have to do for those ones, the even and odd identities, is just think about the location on the unit circle. Like, are the sign values, are they the same sign? Are they opposite signs? What's happening? Okay, so, and you will have to know all of those. So on that first page, you have to know all of those identities, and they'll get easier. But yeah, you'll have to know them, like, as you're doing the problem, how to use them, and so on. So number 1, so it says factor the expressions and use the fundamental identities to simplify. So let's do a few of these. Okay, so the first thing I notice is that in this first expression, I have a tangent squared x in common. So I'm going to factor out a tangent squared x. So when I do that in parentheses, I'm going to have 1 minus sine squared x. Well, I know that 1 minus sine squared is actually a form of my Pythagorean identity. So you can go back and you can look at it. If you have 1 minus sine squared x, or sine squared theta, right, if you just subtract it over to the other side, you're left with cosine squared theta, right? So we know that 1 minus sine squared theta is cosine squared theta. Okay, and then tangent, in general, is sine over cosine, so I'm going to rewrite tangent squared as sine squared x over cosine squared x. And I'm multiplying by a cosine squared x. So I see my cosine squareds cancel, and I'm left with sine squared x. And that's as simplified as it can go. Now the next one, for part B, I have tangent to the fourth, and I have tangent squared. So I can actually factor. And this is kind of strange, but think about it. If I do tangent squared and tangent squared, right, they multiply to be tangent to the fourth, so I'm good. And I put my 1 and 1 here, and they multiply to be 1. And if I check my outer and inner, I have tangent squared plus another tangent squared, which does make 2 tangent squared, so I'm good. Okay, so what I have is tangent squared x plus 1 all squared. Well, this is another thing. So if there's something that's being squared and there's a 1 in your problem, you're most likely using this Pythagorean identities. So you can go back and you can look. Tangent squared theta plus 1 is secant squared theta. Okay, and what I would do is, you know, if you need to write them off to the side and say, okay, I know sine squared theta plus cosine squared theta equals 1. I want tangent somewhere, so I'm going to divide everything through by cosine. Right, you can do that. You can always get those Pythagorean identities right away. When you do that, you have tangent squared theta plus 1 equals secant squared theta, which is what I was saying. So I get secant squared x squared, which, like you would expect, is secant to the fourth x, and that's your answer. All right, now part C is a little bit tricky because now we don't have the same function. Like previously we had tangent to the fourth and tangent squared, so we could factor, which is kind of strange, but it worked, right? But now we have cosecant and cotangent. So I gave you a little hint, and I said, well, how is cosecant related to cotangent? So again, if you need to, off to the side, figure out what the Pythagorean identity is, you can do that. If I want cosecant and cotangent is cosine over sine, right? So I divide through by sine squared. So when I do that, I get 1 plus cotangent squared theta equals cosecant squared theta. So cosecant squared theta is really 1 plus cotangent squared theta. So I'm going to say 1 plus cotangent squared x minus cotangent x minus 3. So I get cotangent squared x minus cotangent x minus 2, which does factor. I don't know if it's going to help us, but let's see. Oops, I forgot my x. You always have to include your argument, right? The x or the theta or whatever it is you're talking about. So we get that. Okay, so nothing happened in this case. I can't go any further. Like I can't replace any of these things. But when we're solving equations eventually, that's actually going to be really helpful. Because if I had had it equaling 0, right, that's going to be where we're solving an equation. We would set each piece equal to 0 and we'd solve. So we will do that eventually where we're solving equations. Actually, you've already done it a little bit before, I think, with your unit circle stuff. So I think you're used to this. All right, number 2, so simplify the expressions as much as possible. So the first thing you notice is that we have 54 degrees and we have 36 degrees. That's like in your problem if you had a theta and an x. Like, they aren't the same thing, so you can't combine them, right? Because they're not the same. So in this case, we can actually get them to be the same thing because these two angles are complementary. I can spell it now, aren't you proud? Okay, so they're complementary. So we're going to have cosine squared of 54 degrees. And let's change the second one. So let's change it from 36 to 54. So what we're going to do is we're going to use its complementary, like its cofunction, right? So instead of cosine, I'm going to use sine. So I'm going to have sine squared of 54. So now we're noticing that we have cosine squared of an angle plus sine squared of the same angle. So that's like cosine squared theta plus sine squared theta, which you should know is 1. That was the Pythagorean identity. Okay, so same idea on this, only now we don't have that they're complementary. We have negative 15 degrees. If it was positive 15, we'd be good though. So let's change this. We know that when we see sine of a negative theta, it's equal to the negative sine of theta. Okay, we're using that one. We're using the fact that sine is odd. So we're going to say that sine of negative 15 degrees is really the same as negative sine of 15 degrees plus cosine of 75 degrees. Don't actually need the parentheses, but we'll leave it. Now we're going to use the fact that they are complementary. So we're going to say negative cosine of 75 plus cosine of 75. And it doesn't matter which one you change. You could have changed the sine to cosine or the cosine to sine. It doesn't matter. So now we see we have negative cosine of 75 plus cosine of 75, so we do get 0. All right, so number 3 says perform the multiplication and use the fundamental identities to simplify. So we can't just bring the square in. Remember, I called that the freshman dream before. We actually have to multiply it out and like FOIL it out, right? Oops, I don't know why I did cosine there. So we're going to have sine of x plus cosine of x. So when we FOIL it out, we get sine squared x. And then the outer is sine of x cosine of x. And then the inner is also sine of x cosine of x, so I'm going to put a 2 there. So we have 2 sine of x cosine of x plus cosine squared x. So even though they're not right next to each other, I do have sine squared x plus cosine squared x, so I do know that that's 1. So I have 1 plus 2 sine of x cosine of x. Okay, and that's as simplified as it can go right now. All right, so then the next one, we're going to FOIL it out. We get 9. Your outer and inner terms actually cancel because one's 9 sine of x and the other one's negative 9 sine of x. Then we get minus 9 sine squared x. Okay, and this one's a little bit harder to see. Okay, but we do see that we have a 9 in common to both of them, so we're going to go ahead and pull it out. When I do, I have 1 minus sine squared x, which is part of the Pythagorean identity. So remember that cosine squared x plus sine squared x is equal to 1. So if I want 1 minus sine squared x, all I'm doing is I'm subtracting the sine squared to the other side. I'm left with cosine squared x. So this is 9 times cosine squared x. And that's as simplified as possible. Okay, number 4 says use the given values to evaluate, if possible, all 6 trig functions. Okay, so I'm going to go ahead and write out all 6. I'm going to say sine of x, cosine of x, tangent of x. The reciprocal of sine is cosecant, so I'll do that one first. Okay, and notice that sine and cosine are both positive. There's only one location where sine and cosine are both positive. That's in the first quadrant. So all of these are going to be positive. So we were given sine was root 3 over 2 and cosine was 1/2. So they're reciprocals. So I'm going to have 2 over root 3, which is really 2 root 3 all over 3 if you rationalize. And secant is going to be 2 over 1, which is just 2. But I still need tangent and cotangent. So remember, tangent is just sine divided by cosine. So it's root 3 over 2 times 2 over 1, which becomes root 3. And then cotangent is it's a reciprocal, so 1 over root 3, which if you multiply by root 3 over root 3, you get root 3 over 3. Okay, so those are the 6 trig functions, 6 trig values. Okay, so we're going to do the same thing for the next one. So we're going to write down sine, cosine, tangent, cosecant, secant, cotangent. Probably should have put these in your notes for you already. Less writing, right? And this time we know that sine is negative The y value is negative, so there's only two locations where that can happen. So it's either this quadrant or this quadrant, so third or fourth. But we also know that secant is positive. So if secant is positive, that means the x value is positive. And then, like I said before, the y value is negative, sign is negative. So where do we have positive, negative? It's in the fourth quadrant. So if you're talking about the signs for the different trig functions, sine will be negative, tangent will be negative, and therefore cosecant and cotangent will also be negative. So just make sure that you have those signs at the very end. Okay, and we know that secant of x is equal to 4, which means that 1 over cosine of x is equal to 4. So cosine of x, if you flip the other side, right, and take its reciprocal, it should be 1/4. So I flip both sides, basically. So cosine is 1/4. So that means if I drew a little triangle, I would go over 1. And my hypotenuse would be 4, right? Adjacent over hypotenuse. But it has to be in the fourth quadrant, so the y value has to be a negative. And if I do my, let's call it y for now, if I do my Pythagorean theorem, I end up getting that y is negative root 15. Okay, so when I talk about these different things, if I talk about sine, remember sine is the y value divided by the r value, so it's negative root 15 over 4. Cosine is the x value over the r value. Tangent is the y over the x, so just negative root 15. Cosecant is the reciprocal of sine, so it's negative 4 over root 15, which rationalizes to negative 4 root 15 over 15. Secant is the reciprocal of 1/4, so it's 4. And then cotangent is the reciprocal of root 15, so 1 over root 15. So negative root 15 over 15. Okay, and those are your different values. Okay, so a little bit harder than the first one because we had to do a little bit of like review from the previous lessons, right, to find the missing value, to find the y value. Okay, but same concept. All right, so some more basic identities. So these say simplify the expression. Note there is more than one correct answer. So sometimes, you know, maybe the answer is secant and you left it as 1 over cosine. I'm not going to be super picky about things like that. I will be picky, though, if it's like really not simplified, if there's like 4 terms and you could have gone down to like one thing, you know, then I will count it off. But for the most part, I'm not too terribly picky. All right, so the first one, so you have cotangent times secant. Well, let's just write what they are with sines and cosines. Sometimes that's helpful. So cotangent is cosine over sine, and secant is 1 over cosine. So you can see that the cosines reduce. So I get 1 over sine, which is the same as cosecant theta. Okay. The next one, secant is 1 over cosine. You're multiplying by sine divided by sine over cosine. So that's a little tricky. So I have 1 over cosine times sine times cosine over sine. So you can see there's lots of reducing here. The sines go away, but then the cosines go away too. So your answer should be 1. The next one, you have tangent, which is sine squared theta, or yes, tangent squared, so sine squared theta over cosine squared theta. And we're dividing by secant, which is 1 over cosine. So we have sine squared theta over cosine squared theta times cosine squared theta. So we cancel, and we get sine squared theta. Okay, the next one, same idea. So we have cotangent of u, so it's cosine of u over sine of u times sine of u, plus tangent is sine of u over cosine of u, and then we have times cosine of u. So we cancel, 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 cancel. So all we have is cosine of u plus sine of u. So be careful. A lot of people will say that that's 1. It's not, because there's no squares, right? So we just leave it. Okay, and then on the next one, we have different denominators. We have 1 plus cosine of x, and we have 1 minus cosine of x. So we're going to go ahead and get common denominators, which we'll do a lot. So on the first one, I have 1 over 1 plus cosine of x, and I want the same denominator as, I want to be able to combine these two fractions, so I'm going to multiply by 1 minus cosine of x on the top and the bottom. And then the second one, I'm going to multiply by 1 plus cosine of x on the top and bottom. Okay, so it's just like if you had, 1 over 2 plus 1 over 3. We're multiplying the first one by 3 over 3, the second one by 2 over 2, right? So that's what we're doing. So the first one, I get 1 minus cosine of x over, its denominator is now 1 minus cosine squared x. And it's the same denominator for the second one, so I'm just going to go ahead and put them all in one numerator. So I'm going to have 1 plus cosine of x. And if you notice, the top, I have negative cosine of x plus cosine of x. And then I have 1 plus 1 is 2. And the bottom, I end up having 1 minus cosine squared. Well, hopefully you guys are getting good at recognizing the Pythagorean identities. 1 minus cosine squared is the same as sine squared theta. So I'm going to have sine squared x. So I have 2 over sine squared. So I would just write it as 2 cosecant squared x. And that's what I was saying. Like, I'm not too picky. Like, I would accept this one as your answer, or the 2 cosecant squared. Some people feel like when it's sines and cosines, it's simpler to them. And some people feel like if you have a denominator, you shouldn't make it a denominator. So it really doesn't matter too much. All right, on the next one, I noticed that I have that weird pi over 2 minus x thing, okay, which is a one of the cofunctions. So when you see that, you're going to replace this whole thing with sine of x. Okay, so we're going to have 2 over 1 plus sine of x minus 2 over 1 minus sine of x. So again, this is one where we need to get common denominators. So we're going to have 2 times 1 minus sine of x all over 1 plus sine of x times 1 minus sine of x. And we're going to have minus 2 times 1 plus sine of x all over that same denominator. So we're going to have 1 plus sine of x, 1 minus sine of x. Obviously, you can save yourself some writing and just put it over one big denominator if you want to. So we get 2 minus 2 sine of x. And then we have minus 2. Be careful, don't forget your other negative. You're distributing the 2 and the negative, right? So we're going to have minus 2 sine of x all over 1 minus sine squared x. So now the 2 minus the 2 goes away. And we have negative 4 sine of x all over cosine squared x. Okay, and you could leave it like that. But when you get to calculus, this is actually going to simplify a little bit more. In calculus, there's something that's going to be, you're always going to be taking the derivative of something, and you'll get like secant x tangent x. This is one of those things. Okay, this is one where if you realize that you can break it apart, you have sine of x. I'm going to put it over cosine of x, and then I'm going to have 1 over cosine of x. See how I'm breaking it apart into separate terms? And I recognize that this becomes tangent, and this becomes secant. So we have negative 4 tangent of x times secant of x. Okay, and like I said, in calculus, you'll see secant x, tangent x a lot. So that's just kind of previewing what you'll have. But it's fine if you have that as your answer or this. It doesn't matter. Okay? All right, so it says you can use graphing calculators or algebraic methods to prove that an equation is an identity. So it says use a graphing calculator to determine if the following equations are identities. If it is an identity, then prove it. Okay, so I already put these into my calculator. I could use my little Wabbit thing online, but it takes me forever to type it in. So let's say I go ahead and I graph the first one. And when I graph the first one, I had something that looked like, and you can do it on your own too, like that. So I put this one in as y1, and then I put the second one in as y2. And when I graphed it, I had almost the same thing, but it was like a shift. Okay, it was here. Where did it cross? Oh, maybe it didn't cross there. Let me draw it on a second one. Okay, it looked like something like this, I think. So if it's not perfect, don't hate me, but it was something like that. And so you could see that they weren't exactly the same because one was just kind of a shift of the other one. Okay, so no, these are not identities. Okay, if you had exactly the same graph, if one overlapped the other one, then they would be identities, and you could do some manipulating to show that they were the true, or show that they were the same. Okay, so it says graph cosine squared x minus sine squared x on a graphing calculator. Notice that this looks like the graph of cosine of x. Okay, but when you graph it, it starts at 1, just like cosine of x starts at 1, and it goes down and back up like cosine usually does. But where it comes back up isn't at 2 pi. And you can find this maximum if you need to. It ends up being 3.14159, blah, 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 pi 1. Okay? So there's something strange about this. It has a different period than cosine of x. So this one has a period of pi instead of 2 pi. So what this means is that we had a horizontal, instead of being 2 pi, right, we went down, we compressed it in to pi. So we had a horizontal compression by 1/2. So what does this mean about our graph? So if you think back to that section that we did before, instead of being cosine of x, if we have a horizontal compression by 1/2, it ends up being cosine of 2x. Okay, so that means that, so this shows that cosine of 2x is actually the same as cosine squared x minus sine squared x. Okay, so that's going to be another identity that we will have. So cosine of 2x equals cosine squared x minus sine squared x. Okay, so we're getting to the point where we're going to be proving that things are true. So these are what I've been talking about. So we're proving trigonometric identities. So there's lots of different ways that you can do this. So different strategies. Number one, you could use algebra and previously proven identities to change one side into the other. So a lot of times I'll write left-hand side, and then I'll get it to equal the right-hand side. Number two, you can express everything in terms of sine and cosine if you get stuck. 3, you can deal separately with each side of the equation. So maybe you start with the left-hand side and you get it equal to like cosine of x. And then you take the right-hand side and you get it equal to cosine of x. Then you can say that the two things are equal to each other. 4, you could look for opportunities to factor an expression. You could add fractions by getting common denominators. You could square a binomial, like multiply things out, or create a monomial denominator. And the monomial denominator is what I'm talking about in this next one. So it says if you see some form of a trig function combined with a +1 or a -1. So maybe you see sine of x minus 1 or 1 minus cosine of x. Okay, those are binomials. Those are two terms. And maybe there's some way that you can make those a monomial. So what we do is we try to multiply by the conjugate. So if you had sine of x minus 1, we would multiply by sine of x plus 1. Or if you had 1 minus cosine of x, we multiply by 1 plus cosine of x. Okay, and that sometimes gives you a Pythagorean identity on the bottom. Okay, and we'll do that in several of these examples. Okay, so this first one. So it says we have 1 plus cosine of x minus cosine squared x all over sine of x. Okay, this is the more complicated side. That's the side that I usually start with. So I start with the more complicated side. So this is the left-hand side. So you can write LHS if you want. Okay. And I notice that I have 1 minus cosine squared x. Okay, and I know that 1 minus cosine squared x is actually sine squared x. So I'm going to replace and see if that gets me anywhere. Okay, now that I have a sine of x on the bottom, I'm going to actually take it into both pieces of the numerator. Okay, all I'm doing here is I'm basically doing the opposite of getting common denominators. I'm breaking it apart into its two separate fractions. So it's kind of like saying if I had 1 plus 5 over 2, it's really the same as 1/2 plus 5 over 2, right? We know that because we do 1/2 plus 5 over 2 is 1 plus 5 over 2 all the time. So we're doing the opposite of getting common denominators, and we're breaking it apart into separate denominators. And when you do that, we get sine of x plus cosine over sine is cotangent of x. And ding, 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 that's the right-hand side. So we're done. Okay, so if you want to write right-hand side, you could do that, or you could just box it in and put a check or something, and I'll know that you're done. Okay, so number 2. So let's say I start with secant of x plus tangent of x, and I'm multiplying by 1 minus sine of x. Okay, this looks a little bit harder. You could change secant x and tangent x into like secant, you could change it into 1 over cosine if you wanted to. Whatever you want to do. I'm going to go ahead and FOIL like it is. So if I FOIL, first outer inner last, I have secant x times 1 is secant x. I have secant x times negative sine of x. So I'm going to have secant x negative sine of x. I'm going to have plus tangent of x is the inner. And the last is tangent of x sine of x. Okay, now I'm going to change it to cosines and sines. So I have 1 over cosine of x. I don't know why I keep doing plus there. So minus 1 over cosine of x with a sine of x on top, right? So it's sine of x over cosine of x if you want to write it that way. Let me go ahead and do that. I'm going to say sine of x cosine of x. And luckily, that's what I have on this next one, right? Tangent of x is sine of x over cosine of x. So there's some canceling that's happening there. Gone, gone. All right, and then I have minus tangent is sine over cosine, and then times sine of x. So now I have 1 over cosine of x minus sine squared x over cosine of x. They have common denominators, so I combine 1 minus sine squared x over cosine of x, which becomes 1 minus sine squared x is cosine squared x. So I end up getting just plain cosine of x. Okay, now this is a problem because I started with my left-hand side and I got that it was equal to cosine of x, but I don't necessarily know that this is equal to cosine of x. Okay, so that's what I was talking about with step 3. Like if you can get both of those sides to equal the same thing, then you'll be good. Okay, so what I can do is, really the nice way to do this is to kind of work backwards. But you could also do right-hand side and then get it to be cosine of x if you wanted to as well. So I'm going to kind of work backwards, and I'm going to say, okay, well, what if I have cotangent of x over cosecant x? That means that I have cosecant is 1 over sine, and cotangent is cosine over sine. Which would be, if you flip it, sine of x times cosine of x over sine, which does indeed equal cosine of x. So see how you can go backwards? And you can get it as well. So kind of tricky, and that's what people don't always like about these identities, because they are a little bit hard when you're first learning them. Okay, don't worry, some of these are pretty easy. All right, so this next one. So I have cosine of x over 1 minus sine of x equals 1 plus sine of x over cosine of x. Okay, this is a red flag. Okay, when you see 1 minus sine of x, every single time you see that, you should recognize that it's not 1 minus sine squared of x, but if it was, that would be really nice for us. If it was 1 minus sine squared of x, then we know that we can replace that with cosine squared. So what we do is we multiply by the conjugate. So if you see 1 minus sine of x, what we're going to do is we're going to multiply the numerator and the denominator by 1 plus sine of x over 1 plus sine of x. Okay, so we're starting with the left-hand side. We're trying to get it to equal the right-hand side. Okay, so we're going to leave that top factor, and you'll see why in a second, because the bottom now becomes 1 minus sine squared x, which we know is cosine squared. So now we're to the point where we have a cosine x and we have a cosine squared x. So when we reduce it, we're left with one of the cosine of x's. So we have 1 plus sine of x all over cosine of x, which is what we needed. So we're good. So that trick will always help you. But that's one, if you don't know that trick, it can be disastrous on your trig identities because you'll keep going around and around in circles, like trying to figure out how to do it. And that was the trick that you needed. Okay, so the next one. So we have secant x plus tangent of x equals cosine of x over 1 minus sine of x. Okay, so you can start with either side. So let's say this time I start with the right-hand side. Okay, the right-hand side is cosine of x over 1 minus sine of x. And I just taught you that when you see that 1 minus sine of x thing, you want to multiply by 1 plus sine of x. So let's try it again. So the top becomes cosine of x times 1 plus sine of x. The bottom becomes 1 minus sine squared x. So we get cosine of x, 1 plus sine of x, all over cosine squared x. We can reduce out by a cosine. So we have 1 plus sine of x, all over cosine of x. And then look to where we're trying to go. We're trying to get it to be secant of x plus tangent of x. So now what we're going to do is we're going to take that cosine into both pieces of the numerator. So we're going to have 1 over cosine of x plus sine of x over cosine of x. 1 over cosine is secant, and sine over cosine is tangent. And that's your answer. That's what we wanted. So that's the left-hand side. Okay, so I highly recommend that you pause and you try some of these. So don't just copy my notes, but I would definitely try a few of these next ones and see if you can get them. And then hit play again and make sure that you're getting the exact same thing. Okay, so the next one. So we have cosecant of x times cosecant x minus sine of x equals cotangent of x. So if you multiply the cosecant in, you get cosecant squared x minus, I'll write it out, but it's going to be sine of x times cosecant x, which ends up being 1, right? Because sine of x times 1 over sine of x is 1. And cosecant squared x minus 1 is actually one of the identities. So again, if you don't know the identities, which, like I said, I never memorized them myself, we write it out, and we say, okay, we want cosecant. If we want cosecant, then I need 1 over sine. So I'm going to divide everything through by sine squared. So when you do that, you get 1 plus cotangent squared x equals cosecant squared x. So that means that cosecant squared x minus 1 is equal to cotangent squared x, which is exactly what you wanted. It was the right-hand side. Okay, this next one ended up being a little bit longer than I wanted, so we'll give ourselves a little bit of room. All right, so the first thing that we notice is that we have 1 over sine of x plus 1, and we have 1 over cosecant of x plus 1. So there's lots of different things that you can do. If you want to, you could multiply the first one by sine of x minus 1 over sine of x minus 1. And you could multiply the second one. If you notice that we just used the cosecant squared x minus 1 thing, you could multiply it by cosecant x minus 1 over cosecant x minus 1, okay? Or you could just get common denominators between the two. It doesn't matter. So do whatever method you want. So maybe you did something completely different when you paused it, and you're like, oh no, what is she doing now? That's fine. You could still get the same answer. So let's say I do it this way. So then on this first one, I'm going to have sine of x minus 1 over sine squared x minus 1. The next one, I have cosecant of x minus 1 over cosecant squared x minus 1. So I know that sine squared x minus 1 is equal to cosine squared x. Actually, hang on, let me write this down. Sine squared x minus 1 is negative cosine squared x. But I had the sign missing. Okay, and the next one is going to be cosecant x minus 1 over cosecant squared x minus 1 is cotangent x. Okay, but when we do this, we can see that we have a problem because we don't have the same denominators. Okay, if I could get them to be the same, that would be good, but they aren't. But they are a monomial, which is good for us because monomials you can bring into both pieces of the numerator. So let's say we do that. So then I'm going to get, I don't know where the best place is to expand this. We'll put it down here. So equals. All right, so this equals negative sine of x over cosine squared x minus the negative, so I'm going to say plus 1 over cosine squared x plus cosecant x over cotangent squared x minus 1 over cotangent squared x, which equals, so I'm going to have negative sine of x over cosine of x. Where am I going here? Times 1 over cosine of x. I don't know if that's where I'm trying to go. We'll try it. See, even I get stuck sometimes. 1 over cosine squared x plus, let's break up the cosecant x. Cosecant is 1 over sine of x. And then I'm dividing by cotangent squared, so dividing by sine squared x over cosine squared x minus 1 over cotangent. So I'm going to have 1 divided by cotangent is going to be tangent, which is sine squared x over cosine squared x. Okay, so what do we have that reduces? So oh wait, hang on. This is a times now, isn't it? I'm sure you guys were all going for that bonus point, getting ready to email me. All right, yeah, that's a times, right? Because we were dividing by cotangent, not tangent. So, okay, so that's good. So we're going to have the sine and sine reduce out. So we're left with 1 sine on top, which then cancels. I don't know if you can tell with my messy handwriting with this. Do you see it? So those are gone. So we have 1 over cosine squared x minus sine squared x all over cosine squared x, which we have 1 minus sine squared x, we're almost there, all over cosine squared x, which is cosine squared over cosine squared, which is 1. So we got it. So that's what I'm saying. You could pick a way that's totally different than what your friends did, and you get to the same thing. Okay, I did this different than what I did on my notes. On my notes, the way I found it, I believe, is by getting common denominators. So I did that. Maybe I did the same thing. But yeah, you could get common denominators. There's lots of different things you could do, and you will end up getting the same answer. All right, so the next thing, and sometimes you do get stuck on identities too. Maybe you get stuck and you have to skip it and then go back to it later. So, I mean, if you get stuck on the test, just do that. And these can be difficult to put on Math Excel as well. So these are things that I would definitely try other examples for. So if you don't have the book, you could at least Google trig identities or something and find some good ones. All right, so this next one, so let's start with the more complicated side. This one's a very easy one, actually. I can already see what it's going to be. So we need an easy one after that last one. That last one was a doozy. All right, so when I pull out the common factor, I get tangent squared x times secant squared x minus 1. And if you think about your Pythagorean identities, secant squared x minus 1 is actually tangent squared. So we have tangent to the 4th x like we wanted. Okay, and this next one, number 8. Let's start with the cosecant x cosine x plus sine of x secant x, and this looks like a good one to make into the sines and cosines. Okay, so when we do that, we have cosine of x over sine of x plus sine of x over cosine of x. And if you notice, for what we're trying to shoot for, we have one term. We don't have like two separate, like a binomial. So let's go ahead and get common denominators. So I'm going to multiply the first one by sine, or no, wait, not sine over sine, cosine over cosine. Multiply the next one by sine over sine. So when I do that, I get cosine squared x plus sine squared x, which is always good, all over sine of x, cosine of x. So I have 1 over sine of x, cosine of x, which I can break apart into 1 over sine of x times 1 over cosine of x. If you think about how fractions work, how you can break that apart, like 1 over 2 times 3 is really 1 over 2 times 1 over 3. All right, so I get exactly what I want, cosecant x times secant x. Okay, and we're good. All right, 2 last examples. I know this is a very, very long video. There's a lot of information in this. All right, so the next one. So I have 1 plus sine of x all over cosine of x. And I noticed that the second denominator has that thing. That's kind of a red flag for us. When we have 1 plus sine of x, we want to multiply by 1 minus sine of x. Okay, and when we do that, we usually leave the numerator in its factored form. We don't multiply the cosine of x in because a lot of times it's going to reduce out. So leave it like that for now. So I have 1 minus sine squared x. So if you notice, 1 minus sine squared x is cosine squared x. So this is what I was talking about. The cosine of x and the cosine squared will reduce down to just 1 cosine of x. We like it when there's just one term on the bottom. So now I have 1 plus sine of x over cosine of x plus 1 minus sine of x over cosine of x. So we get 2 over cosine of x when you combine them, which is 2 secant x. So we're good. All right, and then number 10, you can change things to cosines and sines if you want to. You can get common denominators, lots of things you could do. So let's say I get common denominators. So I'm going to multiply the first tangent by another tangent over tangent. So when I do that, I get tangent squared x over tangent minus secant squared x over tangent. So tangent squared minus secant squared. So that is an identity. Again, if you need to write it off to the side, you can. Sine squared x plus cosine squared x equals 1. If you divide by cosine squared everywhere, you get secant squared x equals tangent plus 1. So secant squared x minus, well, maybe I should do tangent squared minus secant squared is equal to negative 1. So I get negative 1 over tangent of x, which is negative cotangent of x. So I have it in the end. Okay, so that's the end of that section. I know that was very, very long. Hopefully you guys tried some on your own and understood how you were getting the identities. Like I said, I would probably look for examples in the book or online for more trig identities than the ones that are going to be on Math Excel, because I know Math Excel is not very good at giving these on there, and this is a pretty crucial thing for your test, so you will need to know how to do these. Come to office hours if you get confused. I'm always there for you. I will always help you, and I can point you in the right direction if you need some websites or anything to help you with this. All right, thanks.